Today I'm going to talk to you about instantaneous rate of change. So if we just have a look at a graph, for example, to work out the instantaneous rate means we are working the gradient out at one particular point. One particular point on any curve would have the same gradient or rate of change as a tangent through that point. Now a tangent has an equation y equals mx plus c, where m is the gradient. And we can say that the instantaneous rate of change on that curve, or the gradient at the point on that curve, has the same gradient as the tangent on that curve. So, to calculate an instantaneous rate on a curve at any point, we need to know the gradient of the tangent. Now, it's very hard for us to find the gradient of a tangent if we were approximating on a graph. So what we're going to do is we're going to use the idea of a secant. Now, a secant is basically where we're working out the average rate of change. So if I zoom into this sort of small section here, we've kind of got a gradient here. So if we think about the curve, now, for argument's sake, I'll give this a function. Let's suppose it's f of x equals x cubed plus 1. Now, let's suppose I wanted at the point when x was 2. So I want to find the instantaneous rate of this curve at the point when x is 2. I'm going to use a secant, which is a very, very small, or it's a straight line basically between two things. And I'm going to use the idea of the average rate of change to calculate this. With basically the idea being that I'm going to pull this coordinate closer and closer and closer till I get almost on 2. And then once I've done this, I'm going to use this as an approximation for the gradient of the tangent at that point. So let's have a look. Let's make the distance between these 2 points in the x direction 2 and 2.01. So the gap between those 2 points in the horizontal direction is actually just 0.01. Now, in order for me to calculate, excuse me, let me pause the video. Sorry. So in order for me to calculate what those y coordinates are going to be, I will need to substitute when x is 2 into f of x. So 2 cubed plus 1 gives me 9. So f of 2 is 9. And f of 2.01, well, I'll have to use a calculator for that. So it's 2.01 cubed plus 1 gives me, and I've worked it out earlier, 9.1206. Now, using my rise over run, or my y2 minus y1 part, I'm going to do the gradient here of this particular secant, let's call it m1, is going to be 9.1206, subtract the 9 over my change in x, which is 2.01 minus 2. Now this value here gives me 0.1206 over 0.01, which is almost, let's write it down, it's 12.06. So my first average rate of change of this secant is 12.06. Now let's pull that slightly closer and make the gap between these two coordinates only 0.001. So let me clear this graph and I'll do that. Alright, so I've just zoomed in onto this section of the graph here, and you can see I'm using now that x coordinate 2.001, which means the gap in the run direction is just 0.001. Now, if I work out what the y value is, I need to substitute 2.001 into our function, which I've obviously worked out earlier, which is 9. So let's just work that out. So the coordinate's going to be, so f of 2 is obviously 9, and f of 2.001 is 9.012, etc., etc. Now, to work out the gradient, so we'll call that the second gradient of the secant, I'm going to subtract these, which gives me 0.012006 divided by 0.001 gives me 12.006. Now, if we compare these two answers, what we're noticing is that it's actually getting closer to the value 12. So let's just do one more where I'm going to decrease that distance between these 2 points just a tiny bit further. Alright, so I've actually done the working here already. You can see that I've put an extra 0 in here, so that gap is even smaller. And I've worked out that the y value when x is 2.0001 is 9.0012. Now that gradient, if I subtract, gives me 0.0012 divided by 0.006 0.001, there should be an extra 0 in there, apologies, which gives me 12.000600, etc., etc. Now what we're seeing is it's even closer to the value of 12. In actual fact, we use the estimate of 12 as the gradient because this is practically 0, so the gap between these 2 points is so tiny that it's a good approximation for the gradient at the tangent at that point. And that's called the instantaneous rate of change.